Hi y'all, Professor Barber here. This lesson is titled Average Rate of Change of a Function. Functions are often used to model changing quantities. In this lesson, we learn how to find the rate at which the values of a function change as the input variable changes. Upon successful completion of this lesson, you will 1. Be able to compute the average rate of change of a function, and 2. Demonstrate that you understand the relationship between linear functions and the constant rate of change. Roman numeral 1, average rate of change. We're all familiar with the concept of speed. If you drive from Denton to Austin, which is about 200 miles, and the time for your trip was 4 hours, then your average speed or average rate of change is 200 divided by 4 or 50 miles per hour. This does not mean you drove at a constant speed of 50 miles per hour. I'm guessing your speed leaving Denton would be around 35 miles per hour, and your speed on the 35 Express Tollway probably around 85 miles per hour. But overall, on average, it took you about 50 miles per hour to get there. Finding the average rate of change is important in many contexts. For instance, a research pharmacologist might be interested in knowing how quickly a particular medicine enters the bloodstream, or a EE might need to know how processing times are affected by a new protocol. Anywho, for these and so many more situations, scientists need this measurement. For this, we have the average rate of change. The average rate of change of the function y equals f of x between x equals a and x equals b is given by m. Notice m is the slope, equal to little triangle y, which is read delta y, and that delta means little change, divided by delta x. A little change in y over a little change in x is equal to f of b minus f of a divided by b minus a. And remember, you can write f of b or f of x as y. So with that said, this is m, and m is the slope of the secant line between x equals a and x equals b on the graph of a given function f. Let's look at this graph. The graph is presented primarily in the first quadrant. It begins in the second quadrant, increases through the y-axis, and then decreases and then bends upward again and continues to increase. Let's suppose we need an average rate of this function between x equals a and x equals b. How do we do that? To get that value, we just fit a secant line through the points a, comma, f of a, and b, comma, f of b on the function. Then we compute the slope of that line, and then we have the average rate of change of the function. Given f of x equals the quantity x minus 1 cubed, find the average rate of change between x equals 1 and x equals 3. Sketch the graph of f of x and the secant line that represents the average rate of change between the 2 points. The average rate of change is defined as f of b minus f of a divided by b minus a. For this particular problem, we need to find f of the second value is 3 minus f of 1 divided by 3 minus 1. So let's find each of the corresponding function outputs. F of 3, you put in 3 every place there is an x in the equation, so you're going to have 3 minus 1 cubed. That's 2 cubed, and 2 times 2 times 2 is 8. This is also the ordered pair 3, comma 8. Let's find the corresponding y value for x equals 1. So f of 1 is equal to 1 minus 1 cubed. 1 minus 1 is 0. 0 cubed is 0. And that corresponding ordered pair would be 1, comma 0. Let's replace f of 3 with the output value, which we found to be 8, minus f of 1, the output value was 0, divided by 3 minus 1, and then the arithmetic. 8 minus 0 is 8. 3 minus 1 is 2. So the rate of change between, the average rate of change between 1 comma 0 and 3 comma 8 is 4. Let's see what that means. Next part is sketch a graph of f of x. So we'll do that. Now f of x is x minus 1 cubed, and we know from the library of function that f equals x cubed has a graph that is increasing from the third quadrant to the origin and then continues increasing upwards in the first quadrant. So we have a general shape of what the graph looks like. Now let's select a few corresponding function values to see if we can fit the graph. So I selected x equals 0, 1, 2, and 3. Now we're going to find the y values. At 0, in the equation, you would do 0 minus 1 cubed. We already did that. That was negative 1. No, we haven't, but that's okay. That's still negative 1. So the ordered pair is 0, negative 1. I'll plot that on the graph. Let's do this for 1. So you've got, pen's not writing, 1 minus 1 cubed is 0 cubed, which is 0. Okay, so that ordered pair is on the x-axis, 1 comma 0. Let's solve for x equals 2. 2 minus 1 cubed is 1 cubed, and 1 times 1 times 1 is just 1. So the point that corresponds to what we got would be 2 comma 1. So far it doesn't seem to be giving us a shape. Hopefully the 3 helps. So now let's do 3 minus 1 cubed. Ooh, 2 cubed is 8. And that is way up in the first quadrant. Let's connect the points and we should get a shape that looks a lot like the parent function. And we did. So let's go ahead and mark the points, right? 0, negative 1, 1, 0, 2, 1, and 3, 8. We have to now fit a secant line. So in order to fit a secant line, remember 2 points represents a line. It's all you need in order to graph one. So let's recall those points we got earlier when we were solving for the average rate of change. The ordered pairs we got earlier were 1 comma 0 and 3 comma 8. So let's mark 1 comma 0 and 3 comma 8 on top of the graph, and we need to connect those 2 points to get the line. And now we have the graph. The line is the secant line that gives the average rate of change. And we can see that while the function is increasing with a little bit of a curve, the secant line is just a straight line, and that gives us an average rate of change of the function between x equals 1 and x equals 3. For the function f of x equals 4t squared, find the net change and the average rate of change between t equals 0 and t equals 3 plus h. The net change is the difference between where you start and where you end. So we would say that net change, when we're solving for this, is your ending value, which would be f of 3 plus h, minus the starting value, which was f of 3. Let's compute each of those values. For f of 3 plus h, in the given function you have 4, where t was, put in 3 plus h, and square it. As a reminder, 3 plus h squared means 3 plus h times 3 plus h. There is no distributive property of exponents over binomials. And let's continue. This will be 4 times. Multiply the first terms together. 3 times 3 is 9. The sum of the product of the inside terms, which is the product is 3h, plus the outside terms is 3h. That would give us 6h plus, and then h times h is h squared. Now distribute the 4 to each of the terms. 4 times 9 is 36, plus 4 times 6h is 24h, plus 4 times h squared is 4h squared. That's our terminal point or our ending point. Now our initial point or the starting point is going to be evaluated at f of 3. So we'll do 4, and where t was, put in the 3. So 3 squared, that's 4 times 9, which is 36. So let's make the substitutions. We will replace the f of 3 plus h with the expression which was 36 plus 24h plus 4h squared, and then subtract f of 3, which is 36. Some of the 36's cancel, so we get that the net change would be the remaining terms in the expression were 24h plus 4h squared. Please ignore the spaceship landing in the background. Now we are going to look for the average rate of change, and we know that the average rate of change is given by, and so here we want f of 3 plus h minus f of 3 divided by 3 plus h minus, what is that? 3 plus h minus 3. Okay. Guess what? We've already got the numerator term. That turns out to be the net change. And so the net change is 24h minus 4h squared. And in the denominator, we have 3 plus h minus 3, which is h. Oh, so in the numerator, we can cancel and factor out the h's. So we end up with, I'm just going to write A, R, O, C for the average rate of change. And that's equal to 24 minus h squared over h is just 1h. 4h. This is kind of messy, so let me box in net change. Note, linear functions have a constant rate of change, which is the slope.